Okay, so I want to talk about some tools we find useful when we do generic programming, and in particular I want to talk about customization mechanisms that we can use when we do generic programming, and in particular when we want to design interfaces for generic programming or for our libraries. I hope that most of the things that I'll be talking about have been mentioned or even explained before. So it kind of ties together a lot of things and tries to, with all those things that we have in our toolbox from the last few sessions, we can now start to make some nice things which can help us define better APIs. And well, why is this important, or what do we actually want to achieve here? Is that when we, as library authors, want to write generic algorithms, at some point we need some information from the people that use our library to select the best way to do things. So we need to transfer some information from the user of the library to the internals of the library. And this can happen during compile time. For example, sometimes we need to check whether the thing that is provided has the right syntax, does return the right thing, or takes the right arguments, the types. Does the type that is provided have an internal type called type, or stuff like that, which you could check with the concept that we just heard before. Or we want to compute some kind of associated types through something as traits classes, or we use decal type on member functions to find out things about types. Or, of course, we also need at runtime information from the things that were passed through our interface. And this is, of course, depends whatever your thing does. It's very domain specific. And but how do we achieve that in practice? How can we make a customizable interface that is easy to use? So easy to customize for the user of our library, but also has a default, or can have a default implementation if we do not customize it. And here is a list of what we actually would like to have. And I took inspiration from this blog from Barry Brevsin. If you want to read a bit more textual things of some parts that I'll be talking about, have a look at this blog as well. So what would we like to achieve with our interface? Well, I'll leave the first one for last, but I will just talk about the others quickly. So what we would like to have is that the thing we want to customize should be explicitly opt-in. It should not only be opt-in, but it should be explicit, so that when we look at the code, we can say, okay, if we don't do it explicitly, nothing will happen. That helps us when to avoid some unexpected behavior. And it should also prevent incorrect opt-in in our interface. So it should signal some kind of error if we try to do something wrong. And in the best case, the error message should be somehow useful. And the two next, and what I said also before, sometimes it's useful to have a default implementation. So the customization mechanism should also be somehow able to do that. And the two next things tie actually in to what Mauro was saying in the very first lecture, that it should be simple to correctly use something, and it should be hard to incorrectly use something. And in our case in particular, it should be simple to correctly use the customized version, even when a default implementation exists, and it should be hard to use the default implementation even when a customized version exists. And all those things should be somehow expressed in code, so that when we look at it, we can say, okay, yeah, I see what's going on there. And the last point here is that also in programmatically, it should be easy to check that our type or function that we pass into our API should adheres to the things we want from it. So basically check the concept. The first point, which I haven't mentioned yet, is that all these customization mechanisms should be somehow able to be applied on types which we do not have control over. So they shouldn't be intrusive. So some types from a third-party library, you cannot open up and add stuff in there to make it comply to our nice interface. So it should be non-intrusive. But we'll start from the beginning and have a look at how this was done traditionally in all kinds of object-oriented languages. And what the mechanism we have there, and this mechanism is provided by the language, is to have abstract or non-abstract base classes which kind of tell us what the interface should be. For example, it should be a type with a function, member function foo, which is not implemented in this case, but could have a default implementation here. And then you inherit from this base class and you satisfy the interface. And in C++, we use virtual function for this. So there's virtual keyword here, and it's also good practice to use the override keyword so that the compiler gives an error if you override something which doesn't exist in the base, right? And yeah, so let's see how we're doing in terms of our wish list. So, well, it is explicitly opt-in because we need to inherit, so we have to write I inherit from the base, so that's very explicit. It prevents incorrect opt-in, yes, especially if you write override. So if that thing you override doesn't exist in the interface, you know that this is a compile time error. Provides default implementation, yeah, you can do that in the base class. It's simple to invoke, yes. You just have a pointer to the base class, and because it's a virtual function, it will call the implementation from the derived class. It's hard to incorrectly invoke, yes, also that is true, for the same reasons. The code shows the intent, also true, yeah, we can see from the code, this thing inherits from base, okay. It satisfies the interface from the base, and it's easy to verify. We can just check, is the derived type convertible to the base type, or the pointer of it, actually. What it is not is non-intrusive. So it is very intrusive. You have to inherit from something. And if you don't have control over derived, you cannot do it. So that's pretty big drawback, especially in the context that we're talking here, and that's generic programming. But are there other issues? Yeah, there are, and we talked about those earlier before as well. We have virtual function call overhead. We have usually dynamic or heap allocation when we do object-oriented programming in that way. And there's another problem. For example, here I have an interface that's supposed to express something like an array, and it has three kind of things it wants to express. It has a size, which is fine. No problems with that. It has an operator equals, so comparison, which is also fine because array-like, when you inherit from it, it will get downcasted to whatever your derived type is, and this will compile as well. But we have a problem with the last one because here we have a operator, index subscript operator, where we want to get the value at a certain index, but we don't know what we should return because there's no information here in this interface that could tell us what we should return. So, I mean, you know, how could we fix that? Does anybody have an idea? Well, we could stick a template on it, right? We could just do a template T on the array-like, and then we would know, okay, what this returns is a T. Well, you know, this is kind of an interface, yeah? And then maybe my super nice complex array would inherit from this thing, standard complex, you know, specialized on the standard complex. Okay, and then I override the operator. It seems a bit strange, and the virtual call overhead still persists, and we actually don't have one interface. We now have an interface for standard complex, and double, and so on. And there must be a better way to do it, especially for generic programming purposes. And there is, and you have seen it before. And it's not runtime polymorphism, what we were looking at before, right? Dynamic or runtime polymorphism, but static polymorphism. Or one way to do it is through class template specialization. If we already need to somehow specialize this array-like interface, why not just, you know, specialize the whole thing and don't inherit from anything? I mean, there's not much difference. And this is, for example, done in the format library, where there's a thing called formatter, which you, as a user of the library, have to implement for your type T to be able to be printed out. This is actually what you find in the code of format. So, yeah. It's pretty empty. There's not much there. And it says in the documentation that this class would need parse and format member functions, but the default one doesn't have anything, and there's, yeah. So let's look at our table to judge whether this is a good way to do things. Well, it's non-intrusive because I can, you know, implement this formatter for any type T, no problem. It's explicit because I have to specialize this formatter for my type T, that's fine. Prevents incorrect opt-in partially, you know, it could still compile for the wrong T here, but may not do what we want. But we cannot do default, and that's default implementation. That's probably more important, because when you have a class and you do a template specialization, you just need to rewrite the whole thing. You cannot just keep parts of it. It is a new class with the new content. Okay. It's rather simple to invoke, you know, formatter of my type T with the format function, but it's quite easy to incorrectly invoke if you just by mistake put the wrong type here. And this might just work, even if you don't notice it, and you get subtle bugs later on, maybe at runtime even, which is hard to see, hard to debug. We definitely don't see much from this code, so the intent is not really clear, so we have to go into the documentation and read up what we're supposed to do here. And it's also not quite easy to verify programmatically what if our class that we then make is actually adhering to the constraints. Well, we can do an additional concept, and that's basically the only way we can do it. Or Sphene, yeah. So, but there's another way, and this one concerns more free function. Before we just talked about classes, because that was the way we needed to write things because of specialization or inheritance. Right, that's what you can do on classes. But if we want to talk about functions, which we want to customize, we have another thing in the language, and that's being exploited, and that's used quite heavily in the standard library. And you might have seen it from things like standard swap. So who has seen standard swap somewhere or used it? Who? It's gone a bit out of fashion since we have move and friends, but yeah, the main mechanism by which it works is by exploiting argument-dependent name lookup, and we've heard this term before, so I just want to make sure that everybody understands. So, do you remember what this ADL stands for? What it does? Anybody? Yeah, please. That's pretty much correct. Yeah, did everybody get that? Oh yeah, so he said it looks for the function swap also in the namespace of the arguments that you give to the function. And I have prepared a few slides about ADL, so I think it's a good idea to repeat this a bit in more detail because it comes up later also in this talk. So I will quickly do an intermezzo and talk about ADL. Yeah. This is a quote from Josutis, and it reads, "You don't have to qualify the namespace for functions if one or more argument types are defined in the namespace of the function." So kind of a terse representation of ADL, but we'll look in more detail what it actually is. And I think it's useful to look at it historically. Why do we even have a thing like ADL in C++? And it came from the problem that was introduced when Bjarne Stroustrup added namespaces to C. So, you know, in C we don't have namespaces, but in C++ we do have namespaces. And the reason why we have namespaces is like you don't have to prefix every function with my library underscore this function to distinguish it from some other function with the same name. So this is built into the language, so we have namespaces. But then we run into problems. So here, outside of this namespace n, we have an object of type NA, and it's called A. And we can do A++ on it because it has an operator ++, and that's fine because ++ is just like a regular member function, and because we have A, we know it's applied on the type A, so that's fine. But if we do, if we want to print A, we're not sure where to find this function because, yeah, it's not clear. If we don't have ADL, the compiler doesn't know where to look. And so the solution was, yeah, well, whenever we see an unqualified function call, and this one is one in a special form, in kind of an operator form, an unqualified call is just one without adding the explicit namespace where to look for it. Then we should also look in the namespaces of the arguments. And here we have standard cout, so this whole thing is executed in the global namespace. So we look in the global namespace. We look in the namespace std because that's one of the arguments, where one of the arguments come from, and we look in the namespace n, which is where the other argument comes from. That's pretty nifty. So we can write this now, and we're all used to writing stuff like this, this form. But ADL was not only used for is not only used for operators, but it was extended to all functions. And the reason, again, historic reason, was probably that, well, x.foo, the member function, well, we should probably mean the same as foo of x. So, I mean, why should these two things be different? And it's, oh, sorry. So, yeah, instead of writing x : foo of x, we could write foo of x. Should be the same. Well, okay, so that's what ADL does. So when does it apply? When we have a name lookup for an unqualified call, no qualification. And when does it not apply? When it's not a function call. In some rare cases, when you put parentheses around your function, it's kind of an exception. And more importantly, if the thing you call something on is not a function. And we'll use this fact later on, because if you remember, we can have function objects which act like a function, have a function call operator, but they're not functions. So if you use them, they will not be considered, when the ADL does not kick in, basically. In technical terms, how does it work is very involved. there are lots of rules, arcane rules, and if you want, you can read up in the standard. But here is kind of some important facts about this. It looks at all the types after resolving all the aliases of the arguments. It completely ignores any template argument that you might have on your functions. So if your template function argument is from certain namespace, that doesn't play any role, just the argument of the function. The function arguments are considered in no particular order, and then it produces associated types and associated namespaces from those arguments. And again, this is a complicated process, and from all those associated types, it will consider only namespace scope friends. So associated types are, for example, illustrated here. This is a struct A, which has an internal enum E. So if we then call GE, well, E is an associated type of E is A. So it will consider, let's go to F first, because F is a friend. So if I call F on E, it will consider A, the namespace of NA, because F is a friend, but on the G it will not do it. So you see, there's quite some subtleties you have to know if you really want to dig into that. In the end, it does create a set of all these namespaces and finds the best overload that it can match the arguments. But it can also go wrong, and this happens quite often if you and there's a big problem also for generic programming. And there's no real way to prevent that bug, basically. So, and I want to illustrate this with an example, with a quite good example I found on Stack Overflow here. So there's a library 1 which does printing. So it prints something n times. So it takes type nx and prints it n times by calling another function print x, which is just print a single thing one time. And then we have another completely unrelated library 2, which has a class unicorn, and there's a stream operator defined on this unicorn, so we can actually use it for printing. And for some reason, the guy who wrote this class, lib2, found it useful to also declare a print function, which just does something stupid and crashes every time you call it. So now you have, in your application code, in your main, you now use something from library 2 and something from library 1. From library 2 you use this type unicorn, and from library 1 you use the print n. So we want to print unicorn 10 times. And this goes completely awry. This fails horribly. And why is that? Because of ADL. Can maybe somebody tell me why this goes wrong?
Yeah, I mean, you're referencing the lib1 sprint in.
Excuse me?
You are calling print in of lib1.
Yeah, and it goes here, yeah.
I thought I saw it, but no, I don't see it anymore.
Yeah, it calls print n of the library 1, and inside this print n we have another call to a function print.
Ah, okay, that's it, yeah.
And it doesn't go here because of ADL. This one is better in terms of ADL because it looks also in the function in the namespace of x lib2, and then this one is a better match. So it calls this function. And library author 1 cannot do anything about it. If somebody in another library too defines this print, yeah. Okay? So yeah, this was a short excursion into ADL. Now back to customization through ADL, and we call those customization points. And you have seen it, some of you might have seen it from standard swap. So again, those are things that do not incur runtime overhead. And as I said, you might have seen something like this. Using namespace standard, swap A and B. And this kind of incantation repeats over and over wherever you look. And you have to call it like this to prevent some nasty errors. And the way you would then customize your type for this interface is to add a friend function into your struct, which has the same name, swap, and does whatever you need to do. Here it just, swaps the data member. And once you've done it, you can use your generic algorithm can use swap for your type because you've customized it. But this one will call this one through ADL. Does it make sense? Yeah, okay. So remember that standard swap can also handle types without the explicit swap friend function, because if your type is simple enough, is move constructible and move assignable, it can just move it and pretend this was a swap, even though you haven't actually written an explicit swap function. So that's also why here in our table, it is not explicit, because you can write the swap function, which is explicit, but if you don't write it, you might still be able to use this mechanism. So it's implicit, but it is non-intrusive, yes. It partially prevents incorrect opt-in. So here if you, and this is also mentioned in the two next, in these 2 points. So if you forget to do this using namespace standard, it might work, might not work, or does the right thing or does the wrong thing. If you're using standard swap without so if you do a qualified call here, like this, it might fail, because it will not call the ADL, it will not use ADL because it's a qualified call. So this one is unqualified, so it will go here. But if you qualify it with standard, it will not find this function. So there are a bunch of problems with this way of customizing things. And on top of it, it's also not quite clear. If we knew nothing about swap mechanism in the standard library, it's not quite clear that this interface is a customization of something, or that this way of writing things is a customization of something. So verification of the type is not easy to do in this way, because, because we're just, from here we're just deferring to the ADL found function here, and there's no way for us to do any checks here. But we can improve that situation with something called CPOs and customization point objects, and that's also the title of this talk, so I'll go into some detail here. The idea is that the piece that the user needs to specialize is found by ADL and is separated from the piece that the user needs to invoke, and therefore must not specialize and is not found through ADL. So let's take a step back and look at this thing. This is a function, swap2, and it, takes this proven way of doing things, but, ties it together so that we don't forget to use the namespace. Oh, this should be It's using the standard swap, and it's also swap, then unqualified call to swap, so it goes either into the ADL found swap, or it's using the standard swap if it doesn't find anything. So is this function better? Well, not really, because now we have, if we write something like this, using namespace standard2 and then swap2, we're still prone to fall into the ADL trap that this swap2 might go to somewhere else, because for some reason we have a swap2 somewhere else with the right arguments. Okay, there's a way to fix that, and that ties into what I was trying to say earlier when I talked about ADL and when it does not kick in, and that's when the thing you call something on is an object or not a function. Okay, this is a lot of boilerplate code, so let's dissect it in detail one by one. So here we see something we've seen before, is a function which calls swap and brings in the standard swap as well, so we can decide between those two. But the function is no longer a free function, but is now a member function, and a special member function, the function call operator, of a class called swap helper, which can act on two types, A and B, on which you can check some concepts, if you want. We've just before saw the requires keyword, so you can do checks, which you couldn't do before. But how is this better? Now we have a class, and what do we do with this? Well, we then instantiate an instance of this class, and we call this instance, so this is an object, swap. And we do this in a way so that it will, you know, be initialized for the whole duration of the program. Yeah. It's const expert and it's inline, so it stays there. And there's some magic you have to do in order to prevent some subtle bugs with ADL again. You have to wrap it in an inline namespace, and you can add this something which was dubbed poison pill to avoid some bad ADL matches. But once you've done this, you can then define your struct X in the same way as you would have before, but now you can write it in this way or in this way, and both things will do the correct functionality, because the swap is no longer a function but an object. And so this will not do argument-dependent lookup, but it will use the object. Okay? Does it kind of make sense until here? It's quite, you know, involved, and there's lots of things that come together. And it's also sad that we have to do all these tricks to circumvent ADL, but it is what it is. Any questions? I also mentioned that through all this work that we've done, we can now have checks on the types that we use for swap. So we can have swappable constraints. So not everything should be swappable, for example, for some reason or the other. And this is a thing we couldn't have earlier. So Alberto will be happy. Yeah. So did we improve the situation? A little bit, yeah. So we can have default implementation, yeah, because we could add one here, you know. We can have overloads of this operator if we want. Is it simple to invoke? Yes. Is it hard to incorrectly invoke? Yes, because both of these ways work. So we have improved a little bit. Do we really show in the code what we want to do? Well, it's arguable. Still, you know, only this thing we do, and if you're not familiar with swap and you know that there is somewhere a CPO swap, it's not really obvious what we're doing. Yeah, with a separate concept, as I said, we can verify some things about the type, and, you know, put constraints. So yeah. But as you have seen, it requires a lot of code that you have to repeat every time you do new things. And more importantly, this thing, the swap, what do we call swap, or what you would call foo, or whatever your function is that you want to be able to customize, is now globally reserved for all time. If you use this library with another library which also has a name swap in there, there's a problem, and those two things will clash. And this is the reason why people have done tag invoke. Is one of the reasons, the more important reason why people have done tag invoke, which is yet another way of doing the same thing. But it solves a few issues. And the first one is what I just said. It does not claim the name of the thing in the global namespace. So it will only claim one special name, and that name is called tag invoke. The idea of the implementation, I will just, mention this briefly, is you have one special customization point object, the tag invoke, which takes, when you call the call operator on it, which takes another customization point object as first argument, and then does something on it. And there's quite a lot of things you have to implement for this tag invoke mechanism to work. But once you have this, and you can also copy it from the internet, it's not yet in the standard, what is proposed, then you can write your swap function in a simplified way. You could still, write it in this manner, which uses a lot of these, boilerplate protections. You could write it in a much terser form, but that's not the main advantage. The main advantage is now that you kind of opt into the interface in a slightly different way. Instead of writing swap here, you write tag invoke, and the first argument is a tag type from whatever your thing is that you want to customize. And by doing that, you gain a little bit by making it more explicit what you're actually doing. If you see tag invoke, okay, there's something that you have customized, so it's explicit, and it's also I wanted to say, it's explicit what you're doing, and its opt-in is also explicit. And as before, you can use both ways of writing stuff with unqualified call or qualified call, and it will work. So I'm not going through all those, but notice that some things have improved a little bit in my opinion, but there is no yes on everything. So it's not a perfect solution either, but it's much better. It usually requires a similar amount of code than before and is not yet standard. So to conclude all this, since we don't have a language mechanism in C++ to do all this customization on our functions, we have to go through all these hoops in our libraries to write proper customization, which leads to stuff like tag invoke, which is quite good as it goes, but it's still not perfect solution. So if you have just a few functions you want to customize, tag invoke is what you probably want to do. If you want to create a whole type with all kinds of properties for an interface, then you might want to consider other avenues. Okay? So this was a short excursion in the weird world of ADL and CPO. So do you have any questions? Yes, please.
When do you need to do this? Or how do you need that? How do you know that you need to do this? I think I understand the solution, but not what the problem is.
Good question, yeah. So, consider you have an algorithm that is supposed to be generic. And the algorithm, for example, takes a function from the user. Then this function can be whatever, and it's fine. But if this algorithm works on a type for which you cannot write a member function because this type is kind of provided by a third-party library, you want to write a free function for this type that does something special for this specific type. And how does the library pick up on this information? So this is one way to, pass along the information to the library.
So it's more of an interaction between libraries?
It's an interaction between the library and unrelated things on which you have no control. Yeah. And also things you have control over, but you find it probably nicer to write it in this way because it makes the code more readable in some ways, or you can check more things on it. And you can apply concepts as well.
So before C++11, the discussions on concepts were still going on, right? Concepts are being born in 2005, 2006, maybe. Yeah, I mean, it's a very old conversation. And at that time, there was a concept and there were the concept maps. And concept maps were able to say, okay, I need my type to have the plus. And I could say, well, this type doesn't have the plus, but I can mimic it by calling add, for instance, right? So you have this way of doing it. And this might be kind of what they're trying to do here. Concept maps were not implemented because they were basically Turing complete, and people didn't want to get into that kind of weird things. I don't think we are going in a better direction, but anyway, there's something you can do here, right? That's